Hey, my name is Lior. Today I'm going to talk about how to defend attacks as type of reverse engineering attacks against deep learning models. This was started as a side project 2 years ago, and currently we're working on publishing some papers, and yes, it's getting really, really interesting. So, a little bit about myself. I have been working on cybersecurity operation for the last decades, starting from the army and then in the labs. I have been working also in the last 5 years on appliance of different machine learning models on the cybersecurity domain, working closely with industries from telcos, for example, Deutsche Telekom, to solve their problems in fraud detection and in botnet detection. Especially my enthusiasm is for unsupervised learning approaches. Thank you. And I'm also dancing salsa and playing some juggling. It's just my spare time. The talk will be, of course, about some overview and motivation. Then we are going to present the attack flow that we want to deal with. I will present some countermeasures, and finally, I will have some really toy example using MNIST handwritten data set about the attacks and the defense against it. So before we start, just raise your hand, who is familiar with adversarial learning in general? Cool. Who is familiar with deep learning? Cool. And who is afraid that his model will be stolen by an attacker? Okay, so as I expected, many few of you. In this talk, my main goal is to present you this concept, which is highly probable to happen to you if you won't understand the entire environment, adversarial environment that your model is operating in. So, most of you are familiar with machine learning. I won't waste my time on it, but generally speaking, we have an oracle. I didn't present my assistant, which is the Fallout guy that will help me explain my thinking, what I'm presenting. So we have a model, which is let's say an oracle. We're getting instances, and we want to predict. So of course, there are the driving signs, stop signs, and also the camel signs from Beersheba is familiar with. Also, we can apply this oracle on different use cases. Let's say on files, malicious files, that we want to predict if it's malicious or not. During the talk, I will talk mainly about MLP, forward networks. Who is not familiar with deep learning, that were some few. In a neural network, we have an input layer and an output layer. This is, sorry for the ones who are really into deep learning. I call these neurons. Today we hardly talk about neurons, but more as function weights. But generally, the neural networks mainly can capture concepts inside the instances. In this case, we have pictures built upon pixels. The pixels are entering into neurons to the network. And finally, we have the output layer, which present us the probabilities for each one of the classes that we have. So this is just basics. About reverse engineering attack, the general, some taxonomy, having to understand the flow. So we have a service, we have an attacker that wants to extract the model. I will go deeply about how it's being done. And what I want to talk in this slide is about his motivation. The main motivation of the attacker is first to to fool the model. By reverse engineering the model, if I have your model in a way, I can fool it. For example, cause some misclassification to gain some benefits from it. The other concept is more regarding privacy, where the attacker can just steal the model and sell it, or or just reconstruct the data set. These concepts are not science fiction. They are already familiar from research. So Papernote, which is one of the leading researchers in the field of adversarial learning, present the transferability concept, where you can actually reverse engineering the model and fool it using different model totally. So if you have a deep learning model and the attacker is not familiar with that, and he has, let's say, decision tree, he can actually reverse it and also fool the model. This concept is just driven by the problem itself, because the problem has the same decision boundary regardless your model. For data reconstruction, Fredrickson presents that it's possible when you have a trained neural network, you can reconstruct the data set itself. So you can see the original person on the right, the picture, and how we can reconstruct the face back. So this is just some vulnerability we have in the models. In the real world, we have many companies that apply machine learning in their system. It's in cybersecurity, in machine learning as a service, recommendation system, healthcare. What I want you as data scientists to understand is to understand the full scope of your threats. So if you're having a cybersecurity, of course, you're afraid that someone will evade detection. If you have healthcare prediction, maybe some fraud insurance might happen if the attacker will gain your model. So there are wide threats that are possible to your models. This talk is basically about a practical concept of how to defend against reverse engineering attack. Whoever is familiar with adversarial learning is also familiar with the evasion attack, with fooling the model. I won't talk about it. This is really a big topic, researched a lot these days. So the focus is on reverse engineering and practical ways to protect against it. So the attack flow that I just presented, we have a service and we have the attacker. The attacker starts most of the time with a sample data set, or he can generate some synthetic surrogated data set. He queries the model and getting a response with the labels and train the first preliminary model to start with. From this model, he generates instances. So generate instances sounds like very general. So in more detail, we have, from the research that we did, we mapped two types of instance generation methods. The first one is adversarial crafting, where you take the original known data set and you add some perturbation to the instance. And by that, you can explore the decision boundary of the service model. From the other hand, you can also use some algorithms to reconstruct instances or choose instances that your model is not sure of, and then you're doing sort of a line search in your decision boundary model. So basically what the attacker is doing is using, in line search, is using his own extracted model to filter out some interesting instances to query back. So the generate instances query back to the service model, and then going back to the attacker for retraining. And of course, this is iteratively happening multiple times until we have the extracted model. So how the defender, the servers, can actually defend himself. So the first concept is maybe he can manage this reputation context on the user. So if your system is it's very difficult to have user registration. So maybe you can manage user history and understand if the history is malicious or not. It's adversarial, but this is not really working where your platform allows many users to log in, because the attacker can have a distributed attack and train the models using different users. The second concept is, because is a query-based, where actually the attackers is, as we said, is creating instances that are different from the distribution of the original one. And what it can cause some different queries. So the distribution of the attacker query is not similar to the original distribution, and probably our model will be not so sure about these instances, and by that we can raise an alarm. Someone is querying some malicious queries, but what I actually want to talk about today is the model-based defenses, where we can maybe train a model in a manner that he will be preserving some of the will preserve his gradient, or will preserve his knowledge. So we will focus on model, but before that, just mentioning that it's a part of an entire strategy that you can apply in your model where you deploy it. So you can use the user, the query, the model as a part of a strategy, and you can use eventually when you think your model is not under attack, you can use the original model, or you can build a strategy when to use the different countermeasure. So the first countermeasure is just returning the probabilities. You see just no defense at all. So you see the fallout guy just standing in front the wall trying to protect it. The second one, which is we also consider as a baseline, is we call it mass confidence. It's just returning the prediction 0, 1, which is mostly what's happened in the real world, but it depends on the framework. Another concept that you can train your model using adversarial training. This concept is where you use the crafting algorithm that I presented before to generate some adversarial instances, retrain your model, and this results with a little bit more robust model. The main drawback is that you need to be familiar with the attack before. So this is one of the main drawbacks. Another concept is differential privacy. Who is ever familiar, there is a concept in differential privacy, stochastic gradient descent. It's an algorithm where you can train your model while preserving some of the private elements in the model. Essentially what happened is that in each iteration of the model training, we just pick random instances for computing the gradient, and then we add some noise to the loss, and this is our optimization value. So this approach suppose in a way to keep the model a little bit more private. The last concept of defenses is more about having used generalization method to hide the gradient. In neural networks especially, there are many generalization methods because these models actually tend to overfit. What we present here is just to use these methods to extremely generalize the model. It might hurt the model, but also may hide some of the knowledge inside. More specifically, I want to discuss about Dropout. Who is familiar with Dropout? Cool. So the Dropout concept, in each iteration, we randomly drop neurons, and then when we finalize the model, we aggregate the weights of each neuron. This concept, what is the motivation about this concept is because you can look at a Dropout as an ensemble model, because we have many simple models which are with a Dropout, and then we aggregate it to one ensemble model. And ensemble modeling found to be very good for adversarial settings. So this is the main motivation we try this also. In more detail, we use Dropout only in the last layer to have more effect on the output. It's not on the entire network. So if we having some summary about the defenses, so we have no defense, or where we're just returning the prediction itself. Adversarial training, differential privacy, and also the Dropout. This is the new thing that I will present it, that we'll see how it behaves. But the real question is, and this is, I hope you're still with me, because now it's the real deal, is how we evaluate those countermeasures. Because before we simulate everything and try to understand what works more, how we want to evaluate which countermeasure is better than the other. So we present the risk evaluation concept, where we have this trade-off between the affecting the attacker, mitigating the attack, and preserving the original model performance. So we have this risk curve where we have the attacker, and when we use more mitigation, we reduce the attacker accuracy, but from the other hand, we might hurt the original model accuracy. So we have this trade-off, and it can be presented using a very simple risk score where we divide the attacker accuracy divided by the mitigation model accuracy, and this will result with a score, with a risk score. If the risk is low, it means that we hurt the attacker, but we didn't affect too much the original model. So this will be our main evaluation method for that. So if we continue to our example, and this is what I want to focus more today, is we use the example MNIST dataset. We use Clever Hans library. Who is familiar with Clever Hans? Yeah, so cool. So this is a very good library for adversarial learning. Actually, Papernote and Goodfellow are the main contributors in this library. And it's based upon TensorFlow, and there have some nice use cases, and we use it for this demonstration. This is one of the also one of the most important slides in this talk. Is if you want to take something back to your work, is to map your adversarial setting. So you need to go a little bit outside your, as a data scientist, from what you are trying to optimize and to understand the entire setting of your model in the real world. So we assume that the attacker goal is indiscriminate, meaning that he wants to extract all classes. But it might not happen to your use case where, for example, if it's a security-based model, so you have benign and you have different type of benign classes, and you have only one malicious. So maybe you want to, the attackers just want to understand where you distinguish between malicious and benign. Also, we in this specific setting, we have the attacker extraction algorithm, which is the adversarial crafting. The attacker knowledge that we also need to assume is that he has a weaker algorithm than the original service model, and he starts with a preliminary data set. Also, we also assume that the service feedback is explicit, meaning that we return the prediction. On the other hand, it might be implicit, where just the attacker can understand from feedback from the environment what's really happening regarding the model. So in more detail, we have the service model, which is, in this case, MLP with 3 layers, 200 nodes, and we feedback a prediction. The attacker, from the other hand, is a 1-layer network with 100 nodes, and we have a budget. The budget is actually the amount of instances the attacker is querying in each iteration. So it starts from 150 and then continues to 300, 600, and 1200, and so forth. Regarding the countermeasure that they need to deal with the attackers, we implemented a dropout countermeasure with the 0.75 and 0.85 dropout rate, adversarial training, and differential privacy. So this is just to understand how the flows of the attack really go. So we start with the instances that the attacker is creating to extract the model gradient. First, we start. You see specifically in this attack, the attacker starts with a very similar sample that is very similar to the data set. Let's say 1. And as the attack continues, the instances in this specific attack are getting more and more blurred, more and more perturbed because of this specific attack. Okay, so it's just an example. The defender models that we have, as you remember, we have the no defense at all, meaning that it's almost the highest. As I mentioned, the adversarial training really improved the model. This is just a toy example, as I mentioned. So you can see that the no defense at all has, and the adversarial training has the highest accuracy, and the other defenses are a little bit low, which of course it's under We can also add more defense value. For example, instead of dropout 0.75, we can add more or less. It depends. From the other hand, we want also to evaluate the attacker's accuracy. So you can see that as we using a little bit more defenses, the attacker accuracy after implementing and simulating the attack is reduced. So if we don't have defense at all, the attacker accuracy is 0.78. But from the other hand, in dropout, we really reduce the attacker accuracy to 0.66 and also the other dropout. But the main issue, as I mentioned, is not these values, is the cost-effective value, which is the attacker accuracy divided by the defender accuracy. So the results are quite really straightforward. Low value meaning lower risk, and you can see that by using dropout with 0.75, the cost effective of this defense is better. Of course, it's really depends on the ecosystem of how your model is working, and I'm not suggesting that dropout will work on every network. For example, one of the limitations that it's convolutional networks, where dropout has no effect at all on the network itself. So it really depends. Just a toy example where we used MLP, and in MLP, for this example, we really reduce the risk. So take this risk evaluation method and try to play it with it. To summarize, I want you to understand that the models are vulnerable to attacks. Try to understand your environment, who is the attacker, what is trying to achieve, how we can achieve it, and also try to figure out different countermeasures and share it with me if you want, or I can give you some advices. But the countermeasure can be wide range. It can be from the model as I presented, but I think a more straightforward will be managing some user context or understanding the queries of your data set. So investigate also the data set that you allowing your model to predict on. So these are my go away with this. Most of the references you see are written by Papernote regarding this research. There are many papers on adversarial learning, but I think many few that really talked about the reverse engineering part, which is actually the precondition before applying an attack or applying the evasion, the fooling model attack. So I think this is a type of precondition that many of the research are not dealing with. And that's it.
So have you tried combining several or multiple defense mechanisms and measuring the performance of combined defenses?
Yeah, so the question, everybody heard there's a mic. The real issue with working with the other query and user-based defenses is that we need the real data and not the toy data. So it's so in this case, no, I just use the model-based countermeasures. If we want to deploy it, if we will have a live online learning system, I think it's possible, but in this example, no.
For which kind of models, I mean, to which domains did you test your solution?
Mm-hmm. So we tested this approach currently on the image dataset, but also on one security database, Android APKs, for distinguish between malicious or not. This is what we are working currently. The main problem in simulating the attacks on different dataset is the extraction method, because you need, for example, in the security world, it's not only it's not only about creating the instance, but you need that in malicious code. You want it to be compiled and also to perform the attack itself. So there is a great deal of not how to defend, but on the attack. So I can recommend you look at EvadeML, which is a very nice paper that they did it. So We want to use their framework and see maybe if it's possible. But
so is using AvadeML your next step the next step in your research?
My next step in research is basically more formulating more about the equation and how to maybe simulate it as a defender-attacker strategy approach. It's more this is the research. In more applied, yes, it's using maybe the AvadeML. The AvadeML is not using the service is not a neural network. It's a random forest. So it's not really a good use case. But we want to find if you have some nice, interesting use cases where you use deep learning models and you want to test it. So let us know, and we will evaluate it. Yeah.
Thank you. What about using guns for producing more data? Like maybe a network that tries to predict and doing something adversarial between them?
Yeah, so we also examine this approach. The issue with guns is that you really need to tune it a lot. And if you want to focus, this specific research is about defenses and not attacks. But yeah, I think guns is one approach, but it's very different between the domains. And if you want to have a generic attack so the adversarial concept is better, I think. But
well, thank you very much.
Thank you all.